Alright, let's start the section 3 of chapter 5 about Einstein. So take a look at this figure. Can you describe what you notice about Einstein in this photo? He looks thoughtful, maybe even a little mischievous. And that curiosity led to some of the most revolutionary ideas in physics. Born in 1879 in Germany, Einstein was fascinated by the universe from a young age. He was not only brilliant but also extremely curious. So, as a young student, he constantly questioned what others took for granted. Think about that. How often do we challenge ideas that seems obvious? Now, by the early 1900s, Einstein realized that Newton's laws were incomplete. Now let's try a quick scenario. Imagine you are on a smooth moving train. How would you know if it's your train moving or the one next to you? So this illustrates the key idea of relativity. Motion is always relative. And Newton's laws are amazing for everyday speeds. But they can't handle extreme cases like objects moving near the speed of light. So, Einstein discovered special relativity in 1905, which deals with objects in uniform motion. So, the key is that the time and space depend on your frame of reference. Now, if two people pass each other moving at high speed, who is really moving? What do you think? Think about this, okay? Next, general relativity discovered in 1916, which includes acceleration and gravity. So here, gravity is not just a force. It's the curvature of space-time caused by mass. For example, picture a heavy ball on a trampoline. The bend in the surface is like space-time bending under mass. So why is this important? Einstein didn't just refine physics. He reshaped how we understand space, time, and gravity. And his work paved the way for GPS satellites, black holes, and modern astronomy. So, next, let's explore special relativity in detail and see why the speed of light is always the same for all observers. Alright, first take a look at this figure. Here we see two spaceships coasting through space. Now both travelers think the other ship might be moving. But how can they tell? Notice there are no stars or landmarks in this frame. So this is the key idea of the first postulate. So before we begin, here's a quick question for you. If you are in one of these ships, would you know whether you were moving or the other ship was? Now what Einstein realized is that inside a smoothly moving spaceship, there is no experiments you can perform to know whether your ship is moving or not. For example, if you float in the middle of the ship, throw a ball or pour water, everything behaves exactly as if the ship were at the rest. So there's no absolute motion. How interesting. So this means the law of physics are identical for all observers in uniform motion. Whether you are on the left ship or on the right ship in, your experiments will give the same results. So motion is only meaningful relative to something else. And if either spaceship fires its rockets and accelerates, then the crew can feel a force pushing them into their seats. And therefore, acceleration is absolute in this sense. You can detect it. But uniform motion without acceleration is invisible internally. So this is why this version of relativity is called special relativity. It applies specifically to observers moving at constant velocity with no acceleration involved. So the first postulate tells us that there is no absolute motion, only motion relative to something else. And this idea may seem simple, but it completely changes how we understand space and motion. Next, let's see how this leads directly to Einstein's second postulate, which says the speed of light is constant for all observers, no matter how fast they are moving. So look at this figure. Imagine these two spaceships again. Now, if the first postulate is true, how could the travelers figure out who is moving? Can you guess? So Einstein's brilliant insight was that light behaves differently and its speed is the same for all observers. So no matter how fast you are moving, the speed of light in a vacuum is always exactly 3 times 10 to the power 8 meters per second. So even if one spaceship moves toward the light and the other moves away, both measure the same speed. And this is very different from, say, a thrown ball. If you throw a ball while moving, someone else sees the speed as the sum of your speed plus the ball's speed. But light ignores that. Its speed is always the same. And this is what led Einstein to revise Newtonian ideas of space and time. Now, because light is constant, time must adjust for moving observers. So, a clock moving relative to you ticks slower than your clock. And this is called time dilation. And similarly, lengths measured along the direction of motion shrink for fast moving objects. So, this is length contraction. And these effects are tiny at everyday speeds but become huge as you approach the speed of light. So Einstein's second postulate changes everything. Not only is the speed of light constant, but space and time themselves adjust to preserve that constancy. So this is why we can no longer think of time and space as absolute. So next, we will explore some of the startling consequences of special relativity, including how mass and energy are related. Now first, let's look at this graph. It shows how the mass of a moving particle changes as its speed approaches the speed of light. So notice how the curve rises sharply. This is a striking prediction of special relativity. Now let me ask, if you are driving a car at 60 miles per hour, would its mass increase in any noticeable way? What do you think? So at everyday speeds, the effect is so tiny we never notice. But near light speed, it becomes enormous. Remember, Isaac Newton gave us laws of motion and gravity that worked beautifully for centuries. And they still explain baseballs, cars, the moon's orbit, and even spaceflight. But Newton assumed time and space are absolute. And that's fine for slow speeds, but once we approach the speed of light, the predictions don't match reality. So for example, Newton's laws predict that if you keep pushing an object, you can make it go faster and faster without limit. But relativity says there's a cosmic speed limit. Nothing with mass can reach or exceed the speed of light. So Newton's equations are just approximations. And Einstein's equations are the deeper truth that works at all speeds. Now back to the graph. At low speeds, the line is nearly flat. Mass doesn't change noticeably. But as you get to 0.8 times c or 0.9 times c, that means when you get to closer to the speed of light, the curve starts rising quickly. So here c means the speed of light, okay? So this means a particle moving at 90% of light speed has more mass than it does at rest. Interesting, right? Now here's the key point. As mass increases, it takes more and more energy to accelerate the particle. That's why particle accelerators like the LHC require massive amounts of energy just to nudge the particles slightly faster. So let's imagine a clock inside a spaceship traveling at 95% of the speed of light. So to someone on Earth, the ship's clock ticks more slowly. So this is not an illusion. It's a real effect confirmed by experiments. So for example, atomic clocks flown on airplanes tick slightly slower than clocks left on Earth. And the difference is tiny but measurable. So time literally stretches for moving observers. Now picture the same fast moving spaceship. So to observers on Earth, the ships look shorter in the direction of travel. And this effect is called Lorentz contraction. Again, at ordinary speed, it's unnoticeable, just like when you are driving car. But at relativistic speeds, the contraction is dramatic. So together, time dilation and length contraction show that space and time themselves are flexible. They adjust to preserve the constancy of the speed of light. Now here is the energy mass equivalence equation, which is E equals mc square. And this is probably the most famous equation in science. It says mass and energy are two sides of the same coin. Even a tiny bit of matter contains an enormous amount of energy. Why? Because it's multiplied by c square. C is the speed of light, which is equal to 3.10 to the power 8 meters per second. So when you square it and multiply it by the tiny mass, the energy is enormous. So for example, converting just 1 kilogram of matter completely into energy releases about 9 times 10 to the power 16 joules. And that's comparable to the energy of a 20 megaton nuclear bomb. So this principle explains why nuclear power plants and atomic bombs release so much energy. They convert small amounts of mass into energy. And it's also the process that powers stars. So in the sun, hydrogen nuclei fuse into helium, releasing energy as mass is lost. So without this process, Earth would have no sunlight, no heat and no life. So here's the big picture. Newton's law fails at near light speeds, and relativity shows that mass increases with velocity, time slows down and lengths contract. And most famously, mass and energy are interchangeable. E equals mc square. So let's pause for a quick reflection. So if astronauts could travel close to the speed of light, what would they notice about time on their journey compared to people on Earth? Think about it, alright? Now in the next slide, we will see how Einstein took his theory a step further, extending relativity to include acceleration and gravity, leading to general relativity. Now again, imagine you are inside this spaceship, far away in deep space, no planets or stars nearby. And if the ship fires its rockets and accelerates upward, you suddenly feel pressed down to the floor. So here's the question. Does that feel any different from standing on Earth, where gravity pulls you down? It feels the same. And that's the heart of Einstein's equivalence principle. Now Einstein's special relativity, which we just studied, only applies if you are moving at constant velocity. That means smooth, straight line motion. No speeding up, no slowing down. For example, if you are on a train moving smoothly, the physics inside looks normal. But Einstein wanted a theory that included more than just smooth motion. So he wanted to explain motion in every situation, including acceleration and rotation. And that's what led him to general relativity. So the first step was realizing that acceleration and gravity are deeply connected. Now here's where Einstein made a leap. Imagine you are standing in the sailed spaceship far away from Earth. So if the spaceship fires its rockets and accelerates upward at exactly 9.8 meters per second square, you will feel pressed against the floor, just like you feel Earth's gravity pulling you down at 9.8 meters per second square, just like we discussed before. So can you design an experiment inside the ship to tell the difference? Drop a ball, it falls down. Jump, you come back down. So every test gives you the same result. So locally, you cannot distinguish gravity from acceleration. So this is why Einstein said gravity and acceleration are equivalent. Locally, in a small closed environment, they give exactly the same effects. So that's why it's called the equivalence principle. And on Earth, we think of gravity as pulling us down. But Einstein said you could completely describe it as the ground accelerating upward beneath us at 9.8 meters per second square. So in the spaceship, with engines pushing it upward at 9.8 meters per second square, the astronauts feel a flow beneath their feet exactly as we do on Earth. So to them, there's no difference at all. So Einstein's big insight was that acceleration and gravity are really two sides of the same coin. And this was his doorway into completely new understanding of gravity. Alright, now let's see what he discovered. Gravity is not a mysterious force at a distance. It's actually the curvature of space and time itself. Now this picture shows the sun sitting in the middle of a grid, like a stretched rubber sheet. So notice how the grid bends down around the sun. That bending is a way to visualize space-time curving. So here's a quick demo you can imagine. Put a bowling ball on a trampoline. What happens? The trampoline sinks down. Now roll a marble nearby. It curves around the ball. And that's how planets orbit the sun. Not because they are being pulled by an invisible force, but because the sun bends the space-time around it. How interesting. So Newton thought space-time were absolute, like a rigid stage where physics plays out. But Einstein showed that space and time are flexible. They bend, stretch, and even ripple. So the bigger the mass, the more space-time curves. And the sun makes a deep curve, Earth makes a smaller one, and you make a tiny one too. So as physicist John Wheeler put it, mass tells space-time how to curve and space-time tells mass how to move. Now in curved space, the straightest possible path is called geodesic. So think of airplanes flying along the shortest route around Earth. It looks curved on a map, but it's straight on the globe. So similarly, objects in space follow geodesics in curved. Now when you drop an apple, it's not being pulled by an invisible force. It's just following the curve of space-time around Earth. So falling is simply motion along a curved path. Now Earth curves space-time in such a way that all objects naturally move toward its center. So that's why we feel stuck to the ground. So the bigger the mass, the deeper the curve. So a star bends space-time more than a planet, and a black hole bends it so much that nothing, not even light, can escape. Now this model explains Earth's orbit around the sun, the ocean tides caused by the moon, and even the bending of starlight around the sun. So in fact, in 1919, scientists observed starlight bending during a solar eclipse, the first confirmation of Einstein's theory. Now as a summary, Einstein replaced Newton's invisible force of gravity with a new idea. So gravity is the shape of space and time itself. And planets, apples, and even light all move the way they do because they are following the curves in space-time. Alright, now let's look at this figure, which shows Mercury's orbit around the sun. Notice how the ellipse doesn't repeat exactly each time. Instead, the ellipse slowly rotates around the sun. And this effect is called orbital precession. So here's a quick question. Have you ever spun a spinning top and noticed the wobble? So Mercury's orbit does something similar. It shifts little by little over time. But most planets follow nearly repeating elliptical paths. But Mercury's orbit is unusual. Every time it goes around the Sun, the ellipse shifts slightly. It doesn't come back to the exact same position. And over a century, Mercury's orbit rotates by about 574 arc seconds. And that's about 1/6 of a degree. It's a tiny shift, each orbit only about 29 kilometers. But it adds up over centuries. Now, why do you think Mercury is the best planet to show this effect? Because it's the closest to the Sun, where space-time is most curved. So for a long time, astronomers tried to explain Mercury's orbit using Newton's gravity. And to be fair, Newton's law explained most of the shift. The gravitational pulls from Venus, Earth, and other planets accounted for most of the 574 arc seconds. But no matter how carefully they calculated, they were always off by 43 arc seconds per century. And that leftover shift was a mystery for decades. Some even thought maybe there was an undiscovered planet near Mercury. They named it Vulcan, but it was never found. Now, this is where Einstein stepped in. So, when Einstein applied his new theory of general relativity to Mercury's orbit, he found that the curvature of space-time near the Sun explained the missing shift. And his calculation predicted 43.03 arc seconds per century. And the amazing part, the prediction matched observations exactly. So this was one of the first major confirmations of Einstein's theory, and it convinced many scientists that he was right. So Mercury's orbit gave Einstein one of his first big victories. A puzzle that Newton's gravity couldn't solve turned out to be perfectly explained by curved spacetime. So in our next slide, let's look at another dramatic test. Light bending around the Sun observed during a solar eclipse. So let's look at this figure first. It shows starlight passing near the Sun. Normally in daytime, the Sun's glare makes stars invisible. But during a solar eclipse, the Moon blocks the Sun and the stars near its edge become visible. So here's the big question. If the Sun's mass bends space-time, what would happen to the starlight passing close by? The starlight should also bend, and the stars should look like they have shifted from their true positions. So even Einstein said light doesn't travel in a perfectly straight line when it passes near a massive object. Instead, it follows the curve of space-time created by that object. So to an observer on Earth, that bending makes the stars appear slightly shifted outward, away from the Sun's edge. So during an eclipse, astronomers could measure the star's position and test Einstein's prediction. Now even Newton predicted some bending, but his theory said only about 0.87 arc seconds. But Einstein's general relativity predicted exactly 1.75 arc seconds, double Newton's. So the eclipse test was a perfect way to settle the question. If the bending matched 0.87 arc seconds, Newton was right, and if it matched 1.7 arc seconds, Einstein was right. Now in 1919, British astronomer Arthur Eddington led an expedition to photograph stars during a solar eclipse. And when the data came back, the stars near the Sun appeared shifted outward by exactly the amount Einstein predicted, 1.75 arc seconds. So this result was a worldwide sensation. Newspapers declared Einstein's theory triumphs, practically making him a celebrity overnight. And why do you think the world was so amazed? because it was the first time an abstract, difficult theory had such a dramatic real world test, and it passed perfectly. So, since 1919, the bending of light has been confirmed many times, not only during eclipses but also using radio telescopes, which can track how radio waves bend around the sun. And today, these measurements agree with Einstein's prediction to better than 1% accuracy. So, more than 100 years later, general relativity still passes every experimental test we throw at it. So, the 1919 eclipse was the first dramatic proof of general relativity, and it made Einstein a household name. So, let's look at another evidence for general relativity, like the gravitational redshift of light and more recently, gravitational waves. Alright, now imagine throwing a stone into a pond. What happens? Ripples spread outward from the splash, right? So Einstein said something similar happens when massive objects in space move violently. They send ripples through a space-time itself. And these ripples are called gravitational waves. Now these waves don't travel through space. They are ripples of space. So as they pass, they stretch and squeeze distances slightly, like gently tugging on a rubber sheet. And just like light, gravitational waves travel at the speed of light, carrying information across the universe about the event that created them. Now in 1970s, astronomers studied pairs of neutron stars orbiting each other, called binary pulsars. And they noticed the stars were slowly spiraling inward, as if they were losing energy. And Einstein theory predicted that they should radiate energy away as gravitational waves, and the amount of shrinkage matched exactly. So that was the first indirect evidence that gravitational waves are real. Now let's fast forward to 2016. The LIGO Observatory in the US made the first direct detection of gravitational waves. They came from two black holes colliding over a billion light years away, and the detectors measured tiny changes smaller than the width of a proton as space-time rippled through Earth. So this discovery confirmed Einstein's predictions, not just in the solar system but on the largest scale of the universe. So why do you think detecting gravitational wave is harder than seeing light? Because they are incredibly weak and distort space by only a tiny fraction. Now, gravitational waves are produced by some of the most violent events in the universe. For example, when black holes spiral together and merge, they shake space-time like a giant hammer blow. And neutron stars colliding also send out gravitational waves. So in 2017, astronomers not only detected these waves but also saw the light from the explosion, linking gravitational waves to heavy element creation like gold and platinum. So gravitational waves open an entirely new way of studying the universe, not just with light but by listening to space-time itself. See how amazing the universe all around us. Alrighty. Next we will wrap up the overall impact of Einstein's relativity and how it changed our view of the universe forever. So let's summarize what we have learned. First, Einstein started by questioning motion itself. He realized that the laws of physics, including the speed of light, should appear the same to all observers moving at constant velocity. And this leads to some surprising consequences. Moving clock ticks slower. So if you are on a spaceship traveling near light speed, you would age slower than your friends on Earth. Amazing, right? So if you want to be younger, you have to go on a spaceship traveling near light speed. And next, objects shrink along the direction of motion. So from an outside view, your spaceship appears shorter. And also, as velocity approaches light speed, mass increases, which is why reaching the speed of light is impossible. So, while special relativity handles uniform motion, Einstein noticed that accelerated motion, like falling or being pushed, couldn't be ignored. And he realized acceleration and gravity are deeply connected, leading to general relativity. And gravity is the result of how mass bends the fabric of space and time, like a heavy ball on a trampoline. Next, objects move along these curves, which explains planetary orbits and why light bends near the sun. So, this unifies everything. The same principle explains why planets orbit, why tides occur, and why straight shifts during an eclipse. And Einstein theories are not just abstract, they make precise predictions which have been confirmed by observations. So remember, Newton explained almost everything. But Mercury's perihelion advanced 43 arc seconds per century more than predicted. And Einstein's equations accounted for it perfectly. So during the 1919 solar eclipse, stars near the sun appeared slightly shifted, matching Einstein's prediction. And gravitational waves was detected by LIGO in 2016. So ripples in space-time confirmed relativity on cosmic scales. And we can say Einstein didn't discard Newton, he expanded on it. And Newton's laws still work for everyday speeds, but Einstein explained extreme cases. So here we see a natural progression. Special relativity teaches us that time, space, and mass depend on motion, and general relativity shows that gravity is geometry, not just force. And observations confirm these revolutionary ideas, extending Newton's legacy. So imagine if Einstein never existed. Then we wouldn't have to struggle through all these physics problems, right? Alright, everyone. Let's wrap up chapter 5. So, this chapter explored motion, gravity, and how our understanding evolved from Galileo and Newton to Einstein. So, as we go through the summary, think about how each section connects to the last, and how early ideas about falling objects led to orbits, tides, and ultimately the revolutionary insights of relativity. Now, in section 1, we studied Galileo and Newton. So, Galileo showed that all objects fall at the same rate regardless of mass, and introduced the concept of inertia. And Newton formalized motion into 3 laws and described gravity mathematically. So, this foundation is what allows us to predict motion, not just on Earth but throughout the solar system. Next, section 2 applies Newton's laws to orbits. So, orbiting objects are essentially falling around a center of mass. And depending on speed, orbits can be closed or open. And next we learn that tides occur because of differences in gravitational pull across Earth. And friction from tides can even slow Earth's rotation. So this is physics in action around us every day. Finally, section 3 showed us how Einstein extended our understanding. Special relativity revealed that time, space, and mass behave differently at high speeds. But in contrast, general relativity described gravity as curved space-time. So observations like Mercury's orbit and starlight bending confirmed these ideas. So Einstein built directly on Newton's work, showing that the universe behaves in predictable yet fascinating ways. So to summarize, we started with Galileo and Newton, who explained motion and gravity. Then we explored how those principles apply to orbits, tides, and planetary motion. Finally, we saw how Newton's relativity reshaped our understanding of space, time, and gravity. So before the next chapter, make sure to review the practice questions at the end of the chapter. They will help reinforce these concepts and connect the sections together. And don't worry, if you remember the story behind each discovery, the formulas will make much more sense.